Okay, hello today class. Little change of scenery here, but we're going to go ahead and we're going to do our little test review. So test is going to be covering chapters 9, 10, and 13. So why don't we go ahead and work on some of our stuff for chapter 9. So for chapter 9, uh, the big takeaway that we had from that is that we had our our angular acceleration we're usually going to be taking as a constant if we have it at all. So it's either a constant value or constantly zero. And so for these for this stipulation, we have our kinematic equations for rotation are going to be omega f is equal to omega naught plus alpha t. And then we can go ahead and we can take the other analogous equation to be theta is equal to theta naught plus omega naught t plus 1/2 alpha t squared. Um, next, and we can keep going and we can talk about the rest of the equations here where we have omega f is equal to omega I squared plus 2 alpha delta theta. And last but not least, we have that we can take, we have the difference or delta theta is going to be equal to omega naught minus omega z. These are all over 2 times t, where this here, it should be our average of our two. Oh, this is supposed to be positive. Yes, this is supposed to be our average of our two. And so just remember that we use these 5 equations to solve our problems in a way that that is similar to how we solved one-dimensional kinematic problems in in the beginning of the class. Okay, so from before, we also talked about converting linear speeds into uh, ones that are angular. So, like we did before, we got to remember that v is going to be equal to r omega, and that a is going to be equal to r alpha. And then last but not least, we had that x was equal to r theta. And then we took these 3 equations and rearranged them for the respective angular components. And then we went ahead and said that we went ahead and stated that now theta is going to be equal to x over r, which is going to be our arc length basically, or similar to our arc length. And then we have that omega, our angular velocity, was equal to v over r, and then that alpha is going to be equal to a over r. Another equation that we have to remember here is that, or that's going to be useful, is that a radial is going to be equal to v squared over r. And then in this case, when we're talking about it in with respect to angular components, we can plug in what v is equal to, and we get that this is equal to omega squared r. And we saw that from our previous chapters. Okay. We also talked about in this chapter that kinetic energy of a rotating body, or the rotational kinetic energy, is going to be equal to 1/2 I omega squared. And we looked at how if you have translational motion and rotational motion, that you have to split the energy that the object has in between the two. So we then said that for a system that has, say, you have an inclined plane of height h, and you have a wheel rolling down it with some radius r. We said that you have to take, so at the beginning it has potential energy, so you have to take mgh, and then at the end you're going to have to split it in between the two types of energy that you can have. And we looked over in our previous videos how we can go ahead and take and perform this by plugging in what the moment of inertia of the wheel is, or what type of object this is, and we were able to convert v as well into an omega. And you can do this in either direction. Okay, so one thing that we also need to go ahead and remember is the various moment inertias of the different types of bodies that you have. So these are all equations that you probably want to include on your equation sheet. So for a rod with an axis through the center, like so, for a rod like this, where it's spinning, so if you were to take a ruler and spin it around a marker in the center, this is what you would be looking at. Obviously if the ruler was a rod. So what we want to do here is we just know our formulas, and you just want to say that this is 1/12 ml squared. And then if we were to change the axis of rotation and put it around an end, so then for rod around the end, we just say that this rod here has a moment of inertia of 1/3 ml squared. So another couple useful ones here, the rectangular ones are going to be the same for as the ones for the rod, except in this case now you have to take into account that it's a rectangle and no longer a rod, and so for when you're spinning it through its center, this equation gets modified to be a squared plus b squared. And then when it's all along the edge, you wanna multiply it by, say, a squared in this case. Now if you're rotating it, and this is for, say, a rectangle like this, where this is a, and you're rotating it along this edge here. But if you want to rotate it around this edge here, then you want to replace this. So for this one, you want to replace it with b instead of a. Now for a hollow cylinder, we perform the same type of calculation. Okay, so that geometry for this hollow cylinder is going to look something like this. So this will be R1 and this will be R2. And so then in this case, your hollow cylinder's moment of inertia here is going to be the addition of these two, R1 and R2. And then what we can do is we can say, all right, well, what if R1 goes to 0 and we have a solid cylinder? Well, then this term just disappears and you have 1/2 mr R2 squared. And then for a thinly walled hollow cylinder, we can do the opposite, and we'll say that, when R1 goes to R2, well then you're just going to have 2 R2 here, and so then it's going to get rid of this factor of 2 out front, and you're just going to be left with mr squared of the cylinder. And then last but not least, we have to talk about the moments of inertia of a sphere. So for a solid sphere, we're gonna have the moment of inertia here is going to be for a solid sphere. Let's see if I can get a good marker here. So for a solid sphere here with radius r, we're going to have an I that's going to be equal to 2/5 m r squared. And now if we make the cylinder hollow, this 5 turns into a 3. So these are all useful formulas that you should be including on your equation sheet here. Next up, we have to remember how to use the parallel axis theorem, and you just have to remember that IP is going to be equal to ICM plus MR squared. In most cases, you'll see this as a D instead, but it's just the distance from the axis of rotation of the mass that is rotating around your system here. And so you just need to take what the moment of inertia with respect to the center of mass is, and then add on this component as well. And this is a pretty simple theorem with some large amounts of applications. Now, I don't necessarily think that you're going to have to use this equation for mass elements. I think that's a little bit over the scope of this class, so we'll skip past that. But for different moments of inertia calculations, we're usually going to have, remember we said that we had I is equal to r squared dm, and that dm is going to be equal in this case to the differential of the volume times the density here. And the density gets factored out pretty easily, so we just have to pull that out of the equation. And then remember that that dv is going to be equal to dx, dy, and dz. And that should you should be able to integrate this pretty easily for regularly shaped bodies here. For cylinders, you just have to, or for cylinder spheres, cubes, you just have to use the conditions of the geometry to determine the moment of inertia of your object. For chapter 10, there's a couple key equations that you just need to remember. Remember, we talked about how T was going to be equal to F cross R. These are all vectors. And usually this cross product ends up having that this is FR sine theta, where theta is the angle in between the force and the radius in this case. And so usually, in order to simplify this, they just say that this part of the equation here is going to be your lever arm. And so then these torque calculations are usually pretty simple to do. One thing that we also have to remember here is that if we rearrange this equation here for torque, we can see that F in this case, when combined with sine theta, whatever sine theta is going to end up yielding our tangential force here, or F tan. And so then in this case, this is always going to be F tangential times R. And so then you just need to use the magnitude of R, the magnitude of F, and once you combine it with the sine theta, it's going to give you the magnitude of this tangential function, and therefore will yield your torque. Okay, so earlier in the review we talked about analogs. So we're gonna go away from using this as our analog for torque, or our equation for torque, and we can talk about now. We can talk about using the moment of inertia of a rigid body in order to determine a torque. So this is usually for lever arms and stuff like that, for simple torque calculations. But if you have a rigid body and just not a lever and something you're trying to turn, you have to use that your torque is going to be equal to I times alpha. And for different, so you can, in this case, you can have more than one type of torque. So in this case, we can say that the sum of torques is going to equal I equals alpha, or I times alpha. Okay, so once we have found our torque, in these cases, we can go on and talk about the work done by a rotational motion. And usually this is just going to follow the formula that the work done is going to be the integral from two different angles of theta, from theta 1 to theta 2, of the torque times d theta. So if you have the, so what you can do is you can first find your torque here, and then what you can do is then you can plug it in to your work equation here. And then in this case, once you integrate this is going to give you that work, and you can probably just use this algebraic equation. If your torque is not dependent upon theta, then you can just use torque times theta 2 minus theta 1 in the simplest case. But if your torque does depend upon theta, or your torque function does depend upon theta, then you're going to have to integrate this for d theta. And remember, one manipulation that we can do here is when we're talking about what torque is equal, we can plug this in here, and we can make some adjustments to this. So what we can do is we can say then that the work here is going to be equal to, yes, our theta 1 to theta 2. And then when we plug this in, we have I alpha d theta. But now in this case, we can say, all right, well, what is alpha? Alpha is going to be the time derivative of omega. And what we can do here is we can shift this time derivative over to the theta. And so now this equation is going to look like this. And now in this case, we can now say that this is going to be omega here. And so then all of a sudden we have that this is I omega d omega. And now we're not integrating from theta, we're going to be integrating over omega, from omega 1 to omega 2. Because we took the time differential of we took the time derivative of our differential, or our integrand, and we shifted which one is our actual integrand here. So now we have this equation here, and this equation will just yield that I is going to be independent of omega. So then we're going to have 1/2, or I over 2, times omega f, or omega 2 here, squared, plus, well, no, this should be minus omega 1 squared. And so then you can use this equation to find the work done by torque as well. Okay, so next up we have to do a quick review of angular momentum. So we started off talking about angular momentum by saying that L was going to be equal to R cross P, where these are all vectors. This equation then yielded that we had this is going to be R cross MV. And then when we do this, we just have to take the cross product between these two, which is then going to yield us RMV sine of phi. And we now have this R and sine phi here, and that's going to yield us just MV times our lever arm here, or our velocity times our lever arm. So in this case, this is just the equation that you want to use for angular momentum calculations for the most part when you're talking about it in a algebraic sense of the word. But there's a couple things that we can do here. So if we're going to take the time derivative of this equation here, and we're going to get now that dl dt, or the change in angular momentum per infinitesimal time, we're going to end up taking the time derivative here. And if you take the time derivative of this side of the equation, you're just going to end up getting R crossed F, which we know that this is going to end up being our equation for torque. So now we know that that the time derivative of our angular momentum is going to give us torque. So now we've talked about angular momentum as a cross product, but we're also going to have to talk about angular momentum as a for a rigid body. So from before, we have this equation here, right? This is equal to R and V sine phi. And so one thing that we can immediately do is we can say, well, V in this case is going to be equal to R omega, right? And so then this is going to be R squared, or MR squared, right, times V. And now let's just assume that sine of phi, this goes to 1, and we'll say that the angular momentum here is going to be tangential, and we're only worrying about this part here. And so now we're going to have that this equation is going to be omega, and now this here is going to be our moment of inertia, and so then we get that our angular momentum here is going to be equal to the moment of inertia times our angular velocity, or our rotational velocity. And we can now convert this into a vector equation by putting the hats over our two vectors here. Okay, so for a quick review of gravitation, we now have that, we remember that Fg is going to be equal to G m1 m2 over the separation distance squared. So now, if we go ahead and we integrate this equation, we will yield back our potential energy here. And in this case, what we can do is we can say that now that we can say that UG, and we integrate this, we get this is negative G m1 m2 over R. So, but we can do another manipulation with this. So say we set this equal to MA, and we try to find what M is. So in this case, we're going to say that M1 is going to be, say, the mass of the Earth, and we're going to solve for the acceleration near Earth's surface. So we take that this is going to be the radius of the Earth, and so we'll say that this is this, and this should be the massier person, so this is going to be M2. And so then we can divide this out, and we can say that A is equal to G ME over RE squared. And this will end up giving you your value for gravity, and we can now turn this into a G, and this is going to equal 9.81 meters per second squared, like we've been using it in our class. Okay, so next we got to talk about satellites in orbit. So what we're going to do is we're going to take the radial force and equate it to the gravitational force, and then we'll be able to find the velocity for the satellite. And so this is how you get that done. You just go ahead and say that this is G m1 m2 over r squared is going to be equal to mv squared over r. And so then this r cancels with the square. This m is going to be m2 here, so this is going to cancel with this. And then you're just going to get that v squared is equal to g m1 over r. And then v is going to be equal to g m1 over r underneath the square root. So very quickly we were able to derive this circular orbit equation for the velocity. This is, again, just for circular orbits and not for any sort of elliptical orbit. Very quickly we can also derive the period of this, and so these are all useful equations that you should just have pre-programmed into your equation sheet for this test. Just remember again that your t, or your period, is going to be equal to 2 pi r over v, and then you just plug in v here, and this will yield you 2 pi, and then this is going to be r over v, so you're going to have r to the 3 halves here on top, all over the square root of g m1. So then you can go ahead and use that, and then last but not least we have Kepler's laws, and so then you just have to remember what the sector velocity is. And so we talked about this, and we said that dA dt was going to be equal to 1/2 RV sine phi, and this is for the difference in area per time for an angle here, for an angle of the orbit. One thing that we also determined is for an elliptical orbit, this time t for the period, all you have to do in order to go ahead and change this to an elliptical orbit is you just have to replace r with the semi-major axis A. For a review of the talking about spherical mass distributions, please go see my video. I covered that very thoroughly in that video. And then last but not least, we're going to talk about apparent weight. And we talked about this also in the video. So we talked about just how comparatively we accounted for the Earth spinning, and we were able to talk about how a radial changes as you experience a change in latitude. And so as you get closer to the poles, you feel less of that radial force, because that becomes less and less and less, and since you're dividing by it, it becomes bigger and bigger, and so then you feel different types of or not different types of gravity, but you feel a slightly different force of gravity compared at the pole compared to the equator. And so we talked about that in the video as well, and you can go look, rewatch that section of the video if you'd like a refresher on that part of the course. Last, we talked about black holes, and we derived the Schwarzschild radius, or the Schwarzschild radius, whatever your pronunciation is, or you'd like to pronounce it as, and we talked about deriving those equations as well. And so again, The one main equation that we gather from that is that the Schwarzschild radius is going to be equal to 2gm all over c squared. And so once a star collapses through this radius for a constant m, then it can turn into a black hole. Okay. Study hard, or I hope you've studied hard, and I hope you guys get a good grade on your test. Signing off. Bye-bye.